Now let us see how an MRI actually works. See here, so if this is a patient who is standing right now in the room that you are sitting in, right? So this patient's body is not under the influence of any external magnetic field. So what will happen? All the magnets, remember I told you every nucleus in the body is a magnet. All the nuclei in the body, all the potential magnets, they are distributed randomly in space. So they will cancel out each other because they are located in random opposite directions. This patient's body will not have any net magnetic vector because all magnets are randomly oriented. Now what happens? When the patient lies into or on the table of the MRI machine, the patient's body is now under the influence of a very strong external magnetic field B0. Can you see? It is an extremely strong magnetic field with strengths, starting from 0.3 Tesla to almost 3 Tesla, which are used clinically today. So when the patient's body is under the influence of such a strong external magnetic field, what is going to happen? All the nuclei in the body are forced to get angulated in the same plane as that of B0 or external magnetic field. So if you watch carefully here, you would realize that most of the nuclei have aligned exactly parallel to B0, but few of them have also aligned anti-parallel to B0, but they are in the same plane, right? So those who have aligned parallel, they are always slightly greater in number as compared to anti-parallel. Let us cancel off those in the opposite directions. If we cancel off those in the opposite directions, there are still certain nuclei which are excess nuclei which have aligned in the parallel direction. So what happens now? Now the patient's body has developed a net magnetic vector. Can you see this net magnetic vector? Now when the machine starts working, the machine will literally play with this particular net magnetic vector. Now when the nuclei are aligned along the direction of B0 or external magnetic field, they just don't sit straight like this, they begin to wobble. Can you see this movement there? This is called as precession or wobbling. This frequency of wobbling is very important. Why? Because the machine is going to match this particular frequency exactly. If these frequencies match, there will be resonance, and that is called magnetic resonance imaging. This precessional frequency is determined by a formula which is called as the Larmor equation, right, which states that omega, or the precessional frequency of this particular nucleus, is equal to gamma multiplied by B0. Gamma is nothing but the gyromagnetic constant of hydrogen nucleus, and B0 is the strength of external magnetic field. Now let us see how the MRI signal is obtained. MRI image acquisition can be divided into 5 discrete phases. Let us quickly look at them one by one. Pre-scan, excitation, relaxation, acquisition, and computing and display. So let us start with what is pre-scan. Do you remember I just told you that the nuclei in the body are precessing like this or wobbling at a particular frequency? The machine is going to emit radio frequency pulses to the body. If the frequency of the radio frequency pulse exactly matches with the frequency of the precessing frequency of the nuclei, then both frequencies will match. In physics we have studied this is called as resonance, right? That will occur. So therefore, we want to know what is this particular precessing frequency, and the frequency of the radio frequency pulse emitted by the machine should exactly match with it. This is what is done in pre-scan. The machine tries to judge in the body what is the precessing frequency of the various nuclei. Now the machine knows at what frequency this particular hydrogen nuclei they are precessing or wobbling. Next, therefore, it creates excitation. What is excitation? Excitation is when the radio frequency pulse is applied. See what happens. See now, there is it's a nucleus which is oriented in a direction parallel to that of B0, that is along the z-axis. In excitation, a radio frequency pulse is applied to it. Using this radio frequency pulse, some energy is given to that net magnetic vector. So that net magnetic vector takes that energy, and because it has received some extra energy, it moves away from the z-axis. Say for example, it flips down into the xy plane along the x-axis. So what is excitation? Excitation is when a radio frequency pulse is applied to this particular net magnetic vector, and because of this energy which is given, it flips into the xy plane. As long as the radio frequency pulse is being applied, this net magnetic vector will remain in the horizontal plane, or these nuclei will remain in the horizontal plane. This is what is called as excitation. Now remember, now this nuclei, as I said, will remain in the xy plane only as long as the radio frequency pulse is applied. What will happen when the radio frequency pulse is stopped? After excitation, the next phase will start. This is called relaxation. Now what will happen? There are two types of relaxations, T1 relaxation, T2 relaxation. Let us quickly have a look at them. T1 relaxation is also called as spin lattice relaxation. This occurs along the z-axis. Now just see how simple it is. A radio frequency pulse was applied, right? The nucleus was flipped into the xy plane, but now the radio frequency pulse is switched off. So what remains? Only external magnetic field remains, that is B0. So because of the strong external magnetic field, now this nucleus will try and slowly come back into the previous plane parallel to B0. When this happens, look at the yellow arrow there. You realize yellow arrow is the transverse magnetization which is gradually getting lost. Look at the blue arrow. When this vector comes back, the blue arrow is going to gradually increase. What is blue arrow? Blue arrow is nothing but the longitudinal magnetization which is regained. So when the radio frequency pulse is switched off, the net magnetic vector is going to come back to its longitudinal plane. So transverse magnetization will be lost, yellow arrow. Longitudinal magnetization will be gained, that is the blue arrow. So what is T1 relaxation time? T1 relaxation is this coming back of the vector to the Z plane. T1 relaxation time is a time constant. It is defined as the time required for 63% of the longitudinal magnetization to be regained, that is along the blue arrow. Now remember that this T1 relaxation time is different for different tissues, and therefore if we scan at a particular time, each tissue has had a different degree of T1 relaxation, and therefore each tissue appears different from one another in T1 weighted images. So this coming back of vector along the z-axis, this is called as T1 relaxation. What is T2 relaxation? T2 relaxation is also called as spin relaxation. It occurs not along the z-axis like T1, it occurs along the xy axis. Now see, when the vector is flipped into the xy plane by the radio frequency pulse, all the nuclei are in phase. Just imagine you are looking at these nuclei from the top. How are they spinning? Can you see they are all spinning together? This is called as in phase. But what happens when the radio frequency pulse is switched off? Suddenly when the radio frequency pulse is switched off, right? One nucleus spins slowly, other one spins faster, the other one is even faster, other one is even fastest. So they are no longer together. They are spinning at their own pace. This is called out of phase. This dephasing that occurs along the xy plane that we just saw, this is what is called as T2 relaxation, right? So from in phase like this that you can see here, when the radio frequency pulse is switched off, they become out of phase. This is called T2 relaxation. It occurs along the xy axis. T2 relaxation time is a time constant. It is the time required for 63% of the transverse magnetization to be lost. Again, the T2 relaxation time is different for different tissues. So if I take an image here, every tissue has had a different extent of T2 relaxation. So each tissue will appear different on T2 relaxation. So let us compare T1 and T2 relaxation. T1 relaxation is called spin lattice relaxation. T2 relaxation is called spin relaxation. They are two independent processes that are happening simultaneously. T1 relaxation we have studied occurs along the z-axis, that is the blue arrow which is getting increased. So T2 relaxation happens along the xy plane or axis. T1 relaxation time is the time required for 63% of the longitudinal magnetization to be regained, whereas T2 relaxation is the time required for 63% of the transverse magnetization to be lost. T1 relaxation is an overall slower process. T2 relaxation is a faster process. Now what happens during this relaxation, that is T1 and T2, is that signal is emitted out from the patient's body. So when the longitudinal magnetization is getting regained, signal is emitted out. This is captured by the acquisition part of the MRI signal image reconstruction. Similarly, when the T2 relaxation is occurring along the XY plane, signal is emitted from the body, right? So this signal, which is emitted in the form of radio frequency pulses from the body, is picked up by the receiver coils of the MRI machine. This is then given to the computing and display unit, which processes that signal, and an image is actually created. So this is how from pre-scan, where the frequencies are judged, to excitation, when the radio frequency pulse is applied and net magnetization vector or nucleus is flipped from Z to the XY plane, to relaxation, when the radio frequency pulse is switched off. So either relaxation could be along the Z axis in T1 relaxation, or along the XY plane dephasing, that is T2 relaxation. And when this relaxation occurs, the signal is emitted out. This signal is received by the receiver coil, which is then transmitted to the computing and display unit, and the MRI image is finally formed. This is how MRI image acquisition takes place.